Okay, well, let's just get started since we have to switch halfway, and hopefully Wes will show up. Okay, so everybody, welcome to our session on solar system microlensing. Your moderators are me, Bryce, Kalmbach, and Somayeh, Khakpash. She's going to run the slides and keep time. So remember, please keep it to 3 to 4 minutes. We have 4 speakers, so we have a little leeway. And let's go through the next instructions. You can go to the next slide. Okay, so please remember we have a code of conduct. Treat each other respectfully. I think everybody knows it. You should have seen it when you signed up, so please respect it. Okay, next slide. All right, so this is being recorded. If you don't want to be recorded, please turn your camera off. You can type question in the Zoom chat and I'll read it for you. So we don't have a dedicated Slack channel, so all questions should go in the Zoom chat so that they can be part of the recording. And then the recording will be posted later. So yeah, please do show your appreciation at the end when all our speakers have talked. And then at the end of all the talks, we'll have a 10-minute panel Q&A. You can type questions in the Zoom chat, and I'll call on you if you don't mind being recorded. I think that's everything. So we'll switch after half an hour, and you guys can go to another room. But let's get underway, and we'll start with Niall. Go ahead.
Yeah, just sorry, before you start, I'm just gonna say that at 3 minutes, I'm gonna say that it's 3 minutes, but you can go ahead and it can take up to 4 minutes, but at 4 minutes, I'm gonna stop you, okay? Please go ahead.
Hello, I'm Niall McElroy, an undergraduate research intern at Queen's University Belfast. For the past 8 weeks, I've been working on a set of plotting tools to help visualize some of the data from the LSST's Solar System Science Collaborations simulated database in order to develop easy-to-use functions to create uniformly generated plots. One of the main tenets of the package was to make it easy to use and easy to generate insights from by looking at daily or even monthly or yearly data trends and even spreads within said data. On the left here, you can see a generated plot for inclination and semi-major axis made using the program in a hex bin plot with marginals showing the X and Y distributions at a certain point. Attributes such as title and file name and even limits on inclination and semi-major axis can be managed by the user of the package. This package has been published open source on the GitHub repository at the bottom of the slide, with more additions and documentations coming in the current week. Next slide, please. The main question is, how do you handle an order of magnitude more worth of solar system objects? As you can see on this figure, there's an extra order of magnitude worth of objects in each one of the groups when comparing currently known objects with expected LSST discoveries over the 10-year survey length. Well, you can take a three-pronged approach by developing standardized useful range of plotting functions, from scatter plots to 2D histograms to violin and box plots in order to extract insights from the data. You can also use dynamically generated queries in order to add or remove constraints easily for user set variables. And by using user set constraints, you can allow greater customizability of plots by letting the user set, example, inclination limits, limits on the eccentricity or semi-major axis, or filter by date and time, or even just generate a simple bird's eye view plot of the solar system. This package is currently realized with 18 plotting functions, which work based off 8 different queries, 6 of which work based off just user set constraints, whilst 2 of them are dynamically built in order to add or remove constraints for orbital parameters as needed. Exploratory testing, unit tests, and integration tests are also implemented to ensure core functionality. Next slide, please. This and the next couple slides aim to give you some insight into some of the possible plots that can be made using this package. On the left is a 2D histogram plot of objects within the heliocentric distances of 2, 0, and 2 AU. And this plot can give you clear insight into density profiles of asteroids within the min and the maximum user set distances. The plot on the right shows the distances, shows the semi-major axis distances between 0 and 6 AU, and you can even see some of the structure within the plot. Next slide, please. This example plot with user set distance ranges allows a user to probe how detections vary from month to month for different heliocentric distances in a single plot. Next slide. This slide and the next has box plots and violin plots that show your magnitude, heliocentric and topocentric distances and your elliptic beta with different measures on quartiles on the top and the bottom with different quartiles. And on the next slide, please, you can see violin plots.
The time is up.
Okay, sorry.
You want to take a few seconds just to finish it up?
Just gives you better view into the distribution at each point. And thank you very much for listening.
Thank you. Next speaker, Wesley Fraser. Please go ahead.
I don't see him in our room.
Should we go to the next speaker?
Yeah, let's just go to the next one.
Okay. Zach Langford.
Cool, thank you. Yeah, so I've been working on measuring trailed sources in LSST. So kind of the goal here is we want to know things like the flux and the on-sky motion of these trailed objects. And it's useful for understanding population of near-Earth objects and potentially hazardous asteroids. And so for us, what we care about are measuring things like length and angle, centroid, and flux. And there's been some previous work done on modeling trailed sources. So notably from Vera et al. And Fraser et al., which are good for astrometry, and the latter good for photometry. But we have a pretty small time window for alert and prompt processing. So we need to have a very fast algorithm that's also accurate enough to deal with high signal to noise and low signal to noise objects. And so just as a note, we're going to be using the Vera et al. Model here to talk about how we've implemented our model later. Next slide, please. So how do we measure trails in LSST? Well, it turns out that centroid is computed pretty well already by the stack for a large range of trail lengths. So we get that effectively for free. The angle also is easily computed from the already computed second moments, which measure the shape of your object. And so what's left is length and flux. And so it turns out that length, you can compute the analytic formula for the second moments of a trailed source using the Vera et al. 2012 model, which is a Gaussian PSF convolved with a line in a similar way that we convolve a PSF with a point to get a point source. So you can use that model to compute the second moments and then use the numerically computed second moments of a trailed source coming directly out of previous measurements and use a root finder to solve for the length. And so we get a very simple model to evaluate in the root finder, and the root finding algorithm is very fast. And then so that actually gives us the flux effectively for free. So we can use the Vera et al. 2012 model, fix the length, angle, and centroid, and then we can compute the flux with the one-dimensional linear least squares. And so how well does this perform on the next slide? Next slide, please. Thank you. So these are some plots showing the fractional errors in the measurements versus, this is kind of small to see, apologies. So the top plot there is the length errors, the bottom is the flux errors versus signal to noise. So as we can see, The blue is our model, and the orange is the Vera model as kind of like a benchmark for seeing how well our model performs. And so as you can see, even for really low signal to noise, our model performs just about as well as the Vera model. And as I guess another comparison, we have an unweighted second moments measurement on the top versus the adaptive moments which we use that come from the stack. And so the key takeaways here that we can measure trails in science pipelines now. And that our method compares very well to previous measurement methods which require full forward modeling and using optimization tools that are slow. And so this adds actually very little computation time to the measurement pipeline itself on the order of microseconds. Thank you. On the order of microseconds. And then, yeah, I think that's it. Thank you.
Thanks. Our next speaker is Natasha Abrams. Please go ahead, Natasha.
I also saw Wes in the chat appears to be here. I don't know.
I can wait till the end. I was late. That's fine.
Okay.
Thanks.
So, hi, I'm Natasha Abrams. I'm a first-year grad student at UC Berkeley, and I'll be talking about microlensing in the Rubin Observatory. So, gravitational lensing is when you have such a massive object that it actually bends the light of objects behind it in line of sight, creating distorted images of that object. In the case of microlensing, the objects are small with respect to another, small, such as stars and black holes, such that these distorted images are too small for us to be resolved, and instead we just see a characteristic brightening and dimming as they move with respect to one another. We developed a microlensing metric to look at the discovery and characterization efficiency for different OpSims in the Rubin Observatory. We looked at we simulated 4 different timescales of observations, since the lens mass determines the timescale of the event. 0 to 10 days, which are free-floating planets and brown dwarfs, 10 to 30 days, which are low-mass stars, 30 to 100 days, which are stars in general, and 100 to 300 days, which are high-mass stars and compact objects. There are 2 distributions that we simulated. One that's n squared, where n is the number of stars, and all 4 timescales are distributed according to that way, and the based-on-sound model, which leads to different distributions of different timescales. Next slide, please. So we looked at 2 different facets: the discovery, which we quoted in our cadence note, where we looked at the percentage of events with at least 2 points on the rising portion of the light curve, which may be some sort of trigger for other follow-up, and the characterization efficiency, which is, we have 2 different metrics for this: the Fisher metric, which can quantify how well we can measure the event parameters, and the number of points metric, which is the number of points within 2 TE, or Einstein crossing time, which you can think of like duration. Next slide, please. So the big takeaway for the discovery metric was that the footprint of the OpSim has the most impact on the discovery rate. As you can see in the plot on the right, as the percentage of the galactic plane goes up that's covered by the OpSim, the discovery rate goes up. And another interesting takeaway is that the rolling cadence increases the discovery rate for short duration events, since the entire event can occur within 1 observation window, but decreases the efficiency for longer duration events. Next slide, please. So when we throw characterization into the mix, as you can see on the left, these 2, characterization and discovery, where characterization is the Fisher metric here, tend to be aligned, though the characterization is a stricter metric. So there tends to be fewer events characterized than discovered. An interesting metric to look at is the fraction of characterized and discovered events as a function of the number of points in the light curve. And this is an interesting metric because it is not dependent on the location of the microlensing event that occurs in the sky, but rather just the time series of points. And this is a metric we hope to explore further in our Optic Supplement extension of the CAN standard. Thank you.
Thanks. Our next speaker, Wesley, Fraser. Please go ahead.
Hi, everyone. Sorry about that. My cats have a tendency to cause trouble during conferences for some stupid reason. Ever since my thesis project, I've been the guy to go to for doing really faint moving object surveys. And the technique that I've been employing for the last 20 years, because you never get radio thesis, is basically this standard one here: to stare at a field over a night or multiple nights or whatever, calibrate through some techniques. In this case, we're recently using the LSST pipeline. We inject artificial moving sources so that we can understand how well our search does in terms of the detection efficiency. We then shift and stack at rates of motions that are consistent with the object's rates of motions that we're interested in, like, say, the rates of motion of Kuiper belt objects on the ecliptic. And then we look at those stacks and find the things that look like point sources. When you get the shift right, you'll see a nice round thing, and when you get the shift wrong, there will be absolutely nothing in the frame. And here we typically go blind because there's typically 1,000 sources to look at in a frame. Recently, I've been next slide, please. Recently, I've been tasked with the challenge of doing this in the galactic plane, where there's 3 orders of magnitude more stars to deal with, and of course the and despite, no matter how well you do, even with the LSST pipeline's fantastic subtraction routines, you never remove the stars completely. And so the majority of the candidates you get are actually false garbage by many orders of magnitude. And so I've thrown a convolutional neural network at the task, where the inputs are basically a tensor of the different shift rates and angles, and I've trained it on the moving implanted sources. We have thrown a bunch of different techniques at the problem, including ensembles. I'm not quite sure why that arrow is overlapping that, but anyway, here we are. And with these networks, we've been able to reduce the false candidate rate by 3 orders of magnitude, and there's lots of room for improvement without too much more effort. And the result of that is basically double the number of detections, higher detection efficiency, and a magnitude fainter than what we were able to achieve in the same data with the human search. Next slide, please. And so now we're starting to think about this in terms of LSST scale, where the data I've been using come from SuprimeCam on the HSC. Now I'm interested in doing this on an even bigger scale still, because if we can pull it off, we get about a magnitude and a half fainter than we would expect to get from just single detections in the single LSST frames or visits or whatever you want to call them. To pull that off, we will need probably GPUs to do the work, because you can do better, faster stacking on there without spinning up a bunch of hard drives. We'll probably need better, more robust training sets and networks, like, for instance, a ResNet probably is a better choice than the standard sort of convolutional neural networks that I used. We'll probably also make use of cross-lunation linking to get this to work. But again, if we can pull this off, pull that effort off, then we should expect basically 5 times more detections, at least for Kuiper belt objects, than we would from just the straight up LSST frames themselves. And so it's a worthwhile effort. This research bite is basically a fishing expedition for looking for people that want to help me on this, because I don't think I should be the only one looking at it if we actually want to get it done. And I think I'm done and fast. Thank you very much.
Thank you.
Thanks. So let's give all our speakers a hand. Great job, everybody. And we can open it up for questions. I don't see any in the chat. If people want to put them in the chat, that's good. Or you can use the raise your hand feature, and I can just call on you. We have, looks like 8 minutes, maybe a little. Does anybody have any questions? Okay, well, maybe I'll start. I have one for Wes. Oh, wait, was there a question?
Sorry, just wanted to point out that there is one for Wes in the chat.
Oh.
Thanks, Stephanie.
You have a...
No, it's just a comment. I did solar system research in my PhD, and now I'm full-time EPO, but if I still did research, I'd be very interested.
Just going to boldly drop my email in the chat here. If anyone is interested in playing along, send me an email.
I had a question where you say you're using ensembles. Does that mean you're using, you're training multiple networks at a time?
Yeah. Sorry, there's a lot of jargon crap in that frame. The most difficult thing about knowing how to do machine learning is actually getting past the jargon that the community has put up. It's a big barrier. Anyway, so ensembles are the case where you train multiple separate networks and then merge the outputs. So in terms of the binary classification, you merge the probability of false or real kind of deal, and then apply the selection on that. And the idea there is that training is never perfect. You never actually achieve the global minimum in your likelihood or classification probability or whatever. But on average, you get pretty close. And so if you can train, in this case, 10 separate networks and merge the outputs, then you are probably going to get closer to the correct answer. And so the performance is, in fact, an order of magnitude in performance was found just by merging the outputs together, which was awesome. Yeah. Good question.
Thank you. Does anybody else have any other questions?
Yeah, I have a question for our first speaker. I really like the idea, to make some general visualization tools for LSST data, especially at scale. Are you planning on having something that's interactive as well, or are you preferring to simply have that as kind of matplotlib wrappers?
In an ideal world, obviously I'm working on this on a 8-week internship, which ends at the end of this week, but ideally it will be open source, and ideally I might add some stuff like Booker stuff that is sort of interactive, or like orbit propagation maybe, and stuff like that, to add a bit of interactivity to it. Obviously it will be open source, so there will be an opportunity if people want to also merge their own stuff in, if they want to help sort of build it out. But the real idea was sort of to get a sort of set of data visualization tools that are just sort of plug and play, that can then just be used to get a sort of set of default plots, or to look at sort of trends over, say, a month, a year, or just a week. And just sort of on that sort of order, to have just easy, rather than having someone have to go in every time and sort of write all the code to do it themselves.
Okay, thank you.
And it looks like we have a question for Zach from Melissa. Do you want to go ahead and ask your question?
Yes. At the beginning of your talk, you said that the some of the measurements you get for free from the LSST pipeline. Are there other processes that you have used to calculate the trail length that can be applied to other data sets? Can some of your later sets be applied to other data sets that are not LSST?
Sure, yeah. I mean, so realistically, what you need is just a measurement of the adaptive moments for this method. And then other than that, the Vera et al. 2012 model is effectively, a full forward model for doing that. So that's the other thing that's implemented in LSST. So if you don't have adaptive moments or centroiding, I guess, then you'd want to use the Vera et al. 2012. And then if you want really good photometry, you'd use the Fraser 2016.
Okay, thank you.
Looks like we still have time for another question, if anybody has one.
I actually wouldn't mind asking a question of Zach. Have you seen something that came up the other day, which is someone asked me, talking about the machine learning stuff that I'm doing now. By the way, hey, machine learning, I don't think it is a be all end all solution for humanity's problems, but I'm just wondering, like, I look at images like this and I see basically a regression problem. And I wonder if a network trained on images like this might be able to get you an elongation that is sort of a bit more agnostic of signal to noise. Like your results are fantastic. I think the curves right down to an SNR of 10 are amazing, actually. But I guarantee you that the network, once trained, will still be faster, even on a cell phone, than it would be to do what you're talking about here. So do you know if anyone's actually exploring that?
Not that I know of. Mario, do you have any comments on that?
Yeah, I don't know either. I think that the reason why I went with this approach is because this is important to run fast in prompt processing pipeline. And then I think the biggest thing that Zach discovered here is that with the adapted moments, which the stack already measures, we can basically measure trail lengths with almost no loss of precision relative to direct fitting by just doing an analytic transformation. So it's like one equation and you're done, which is kind of amazing. But then we understood why in the end. So we haven't explored beyond that, because this is kind of the fastest I think we can get, given what stack already has to do.
All right. Let's thank our speakers one more time. And then feel free to check out another room, and then we will get ready for our next go around. Thanks again. Okay, we'll get started again. Looks like our numbers have stabilized. We have some new additions. Okay, so everybody, welcome to the solar system and microlensing session for the research bytes. Myself and Somayeh are your moderators. And go ahead on the next slide. So just a reminder, if you are just joining the session, remember everybody's signed a code of conduct, so please respect it and respect each other. Okay, go ahead to the next one. So the way this will work is everything's being recorded. So if you don't want to be recorded, remember to turn your camera off before you, now that you're in here. You can write a question in the chat and I'll read it out if you don't want to be recorded. Otherwise, you can write something in the chat and I can call on you, or you can raise your hand. So questions will all come at the end. We're going to let all our speakers talk, and then we'll have a panel Q&A once everybody's gone. So I think we're ready to go with our first speaker.
Hello, I'm Niall McElroy. I'm an undergraduate research intern at Queen's University Belfast. So for the past 8 weeks, I've been working on a set of plotting tools to help visualize some of the data from the LSST's Solar System Science Collaboration Simulated Database in order to develop easy-to-use functions and create uniform generated plots. So one of the main tenets of the package was to make it easy to use and easy to generate insights from by looking at daily, monthly, or yearly data trends and spreads within said data. On the left, you can see a generated plot for inclination versus semi-major axis made using the program in a hexbin plot. It has marginals on the side of the X and Y axis that show distributions at a certain point, and attributes such as title and file name, and even limits on the inclination and semi-major axes can be managed by the user in the package. This package has been published open source in the GitHub repository at the bottom of this slide, and more additions and documentation are coming in this current week. Next slide, please. The main question is, so how do you handle an order of magnitude more worth of solar system objects? So in this figure, it makes it abundantly clear how every group of object has an extra order of magnitude when comparing the currently known objects with the expected LSST discoveries over the 10-year survey period. Well, you take a three-pronged approach by developing a standardized and useful range of plotting functions, from scatter plots to 2D histograms, and to violin plots and box plots in order to extract insights from the data. So secondly, you can use dynamically generated queries in order to add or remove constraints easily through user set variables. And thirdly, by user set constraints, you allow a greater customizability within the plots by letting the user set limits on, for example, inclination, limits on the eccentricity or symmetry axis, or just filter by date and time. This package is currently realized in 18 plotting functions, which work based off 8 different queries, 6 of which are just simple queries with user set constraints, whereas 2 of the queries are dynamically built in order to add or remove constraints for some orbital parameters as needed. There is testing implemented to ensure core functionality. Next slide, please. Sorry. This and the next couple of slides aim to give you some insight into some of the possible plots that can be made using the package. On the left, you have a heliocentric 2D histogram plot with objects with a heliocentric distance with a minimum of 2 and a minimum of 0 and a maximum of 2 AU. And the plot can give you clear insight into some of the density profiles of the asteroids within the minimum and maximum user set distances. The plot on the right shows the semi-major axis between 0 and 6 AU, and it even allows you to see some of the structure and density spreads within said range. And next slide, please. This example plot has user set distance ranges and allows you to probe detections, how they vary from month to month for different heliocentric distances. Next slide, please. On this slide, you have your box and your box in plots, which show different quartiles of data. And on the next slide, please, you can also see your violin plots, which give you better insight into the distribution at a certain point. Thank you very much.
Thank you. Our next speaker, Wesley Fraser, please go ahead.
Hello. So ever since my thesis, I've been doing these deep object, moving object searches that basically uses the same technique I've been using for the last 20 years to stare at a field with a wide field camera and take repeated imagery. And then after calibrations, which recently we've been using the LSST pipeline and injection of artificial sources for moving object detection, we shift and stack the imagery at rates of motion consistent with the expected rates of objects of interest. We stack them and then we manually search them, basically looking for point sources, because when you get the correct rate of motion, objects show up as nice round things. When you get the wrong rate of motion, they don't show up at all. And this works out quite well, even in large data sets. When you're looking at blank regions of the sky, even when you go blind, blinking a few thousand sources, it's pretty good. But recently I've been tasked with doing this in the galactic plane where there's orders of magnitude more stars. And even when you get the best image abstraction routines possible, like with the LSST pipeline, there's still all kinds of residuals that, when in these shifted and stacked frames, totally dominate with false detections, totally dominate the real things. Next slide, please. And so to handle this, I've thrown machine learning at the problem. Basically, a binary classification tool was generated that tells you what the probability of this detection being a good moving object or not actually is, where we use as input a tensor of basically a stack of all of the different rates of motion in a 3-dimensional image tensor. And we pass it through something that looks like a pretty standard convolutional neural network, with the only real fancy thing about it is using ensembles, which we can talk about. And when you do this well, we found a 3 order of magnitude decrease in the false positive rate, which was astonishing. But it basically took the problem from untractable to totally doable by a human. Now I can search a single night worth of, an entire night's worth of hypersur PrimeCam data in a few hours by eye. We also netted twice as many detections. We got a magnitude fainter in depth and a 50% higher peak detection efficiency. So it worked out pretty well. Next slide, please. Now we're starting to think about this for the LSST, given the success that we had. We're still not there yet. Computationally, this is much harder than a single night with the HSC. So we're going to have to go to GPU tricks, which have been explored by Wyden et al. And a couple others. We're also going to need better false positive rejection, which is probably going to come from a range of different sources, including a more robust training set, because we only had one night worth of data to train on in any given search. Alternate network structures will be used, fancier, deeper networks and all. And then, of course, we can take advantage of cross-lination linking to really throw away some of the nefarious false positives. And if my experience with this is correct, we should see about 1.5 magnitudes fainter overall depth and about 5 times more moving objects. And it's especially true for the Kuiper belt objects, which have very steep luminosity function. So I think the effort is worthwhile. 5 times return on an already big sample would be quite an astonishing thing. And this is a fishing expedition for me. If there's anyone that wants to participate in studying on how to make this work, please reach out, because it's not going to be a one-man show here, and I'd very much appreciate the help. Thank you.
Thank you. Our next speaker is Zach Langford.
Thank you. Yeah, so kind of going off of Wesley's talk, I'm measuring things that are moving a little bit faster that make trails in images. So we're interested in measuring the flux and the on-sky motion of trailed objects. And in particular, the way that we parameterize this is with length, angle, centroid, and flux. And so there's been some previous work that's gone into modeling and measuring trailed sources, notably the Vera et al. 2012, which uses a model fitting where you're fitting a Gaussian PSF convolved with a line. And then the Fraser et al. 2016, which gets very good photometry. But the problem for LSST is that both of these methods are a little too slow for prompt processing. So we have a window of about 60 seconds to get out our alerts. So how do we do this in LSST? On the next slide, please. A couple of these we get for free. So the stack already does a great job. The LSST Science Pipelines stack does a great job of computing the centroid. And then from the adaptive moments, we can compute the angle pretty easily. And then so that leaves us with length and flux. So it turns out you can solve analytically what the adaptive moments of a trailed source model using the Gaussian PSF convolution model. And then you can compare that with the numerically computed adaptive moments and use a route finder to solve for the length of the trail. So route finder, this method allows us to not have to touch any pixels, and we can use a fast route finding method. And then so this effectively gives us the flux almost for free. We just need one evaluation of the Gaussian PSF convolution model. So if we fix the length, angle, and centroid, we can then use linear least squares. We have a one-dimensional problem we can solve for the flux. So on the next slide, how well does this perform? Pretty well. So we compared this with using unweighted second moments, and then also directly with the Vera et al. Model. And so the plots here are on the top, the length, the fractional errors in the length, and the fractional errors in the flux on the bottom versus signal to noise. So as you can see, for almost all signal to noise, we get pretty comparable accuracy and variances in our measurements for our model versus the Vera et al. Model. So kind of the takeaways here is, one, we now measure trails in the science pipeline, and that our model compares very well with the actually fitting a full forward model for trailed sources. And this actually adds very little computation time to the measurement pipeline, on the order of microseconds, versus fitting a forward model, which adds upwards of 10 milliseconds, depending on size of the image and whatnot. That'll do it for me. Thanks.
Thank you. Our next speaker is Natasha Abrams. Please go ahead.
Hi, I'm Natasha Abrams. I'm a first-year grad student at UC Berkeley, and I'll be talking about microlensing with Rubin. So gravitational lensing is when you have such a massive object that it bends the light of objects behind it in our lines of sight, creating distorted images of that object. In the case of microlensing, these objects are smaller, like on the order of stars and black holes, such that we can't actually resolve these distorted images, and instead we see a characteristic brightening and dimming as they move with respect to one another. So we made a microlensing metric to explore the discovery and characterization efficiencies for different OPSIMs for LSST. We looked at 4 different timescales, since the duration of a microlensing event is determined by the mass of the lens involved. We looked at 0 to 10 days, which is characteristic of free-floating planets and round dwarfs, 10 to 30 days, which is like low-mass stars, 30 to 100 days, which are in general stars, and 100 to 300 days, which are high-mass stars and compact objects. We also looked at 2 distributions. We looked at 2 distributions of these events, n squared, where n is the number of stars, distributing all 4 of these timescales at the same way, and the Besançon model of the galaxy, distributing these at different times, in different ways. Next slide, please. So first we looked at this discovery criteria, which detects at least 2 points on the rising portion of the light curve. We want to see what percentage of simulated light curves we can detect in this way. This was explored in our cadence node. And then there's the characterization. Which we have 2 different metrics. There's the Fisher metric, which quantifies how well we can measure the event parameters, and the endpoints metric, which is the number of points within 2TE or Einstein crossing time, which you can think of like duration. And this is interesting because this way we can see how many events the Rubin Observatory can analyze on its own. Next slide, please. So the main takeaway from the discovery criteria is that the footprint of the OPSIM has the most impact on discovery rate. As you can see in the plot on the right, the discovery rate is a function of the percentage of the galactic plane covered. You can see that the more the galactic plane that's covered, the higher the discovery rate. And in this plot, each point is a different OPSIM, with each shape being a different family of OPSIMs. Another interesting takeaway is that the rolling cadence increases the discovery rate for shorter duration events, since the entirety of the event can occur within one observation window, but decreases for longer duration events, which might not be covered entirely in that observation window. Next slide, please. When we throw characterization to the mix, as you can see on the bottom left, we have characterization by discovery, and the characterization here is the Fisher matrix criteria, and these are generally aligned, though the characterization is a slightly stricter criteria, so there are fewer events characterized than discovered. We can also look at the fraction of characterization events that are characterized and discovered as a function of the number of points in their light curve, and this is an interesting metric because it doesn't depend on where the events are happening on the sky, and rather just the array of times that are fed into the metric. Thanks. Yeah, so we hope to explore this further in our FJ supplement extension of our cadence node. Thank you.
Thank you.
All right. Thanks to all our speakers. Let's give them a round of applause. Thanks, everybody. Okay, so let's open it up to questions. So you can either drop it in the Zoom chat, or you can use the raise hand function here on Zoom. So do we have any questions? I guess I'll start with one for Natasha. How many microlensing events total do we expect to see with the LSST in Rubin?
So that's an interesting question. It's highly dependent on which OPSIM ends up being chosen. Or rather, in this explanation, we're just comparing different OPSIMs. And so I can't give you an exact number, but like for the longer duration options, when we were looking at for the longer duration microlensing events, when we were looking at the n-squared distribution, we could recover nearly all of them, whereas the for the shorter duration ones, it's closer to 50% or less, or fewer.
And on the order of hundreds of events or tens of events?
Oh no. I believe between like tens of thousands and hundreds of thousands. So if Somayeh, if you happen to remember a better number.
No, that's good. I was just wondering the scale. That's cool.
Yeah. On the scale of like tens of hundreds of thousands.
Okay. Do we have other questions? Anybody? Okay, last call. All right, let's thank our speakers one more time. Everybody, great job. Very interesting talks. Glad we could hear them all. All right, so I think that concludes our session. Thanks everybody for joining us. So the recording will be up there soon, I guess. So if you want to rewatch any of the talks, you can do that. Thanks everybody.
Thanks, Bryce.
Thank you. Bye.
Thank you.